Okay, here we're going to do a quick overview of integration, just so that you know what an integral is, so that when we do them in the next unit, you'll know what we're talking about. Basically, an integral is finding the area under a curve. And by the area under a curve, we mean the distance from the curve itself down to the axis. So it's the shaded area in here. That's what we want to find. And we'll find it from some point on the x-axis A to some other point B. And we'll have some function f of x that describes this curve. Note we in general cannot use simple geometry because this will be some arbitrary curve, so we can't break it into simple geometrical shapes. So the way we're going to do this is first take this area and divide it into rectangles. And we'll start by dividing it into 5 rectangles. That approximates the area under the curve, and we can then calculate the area of each of these rectangles because the height of the rectangle would be the function of the value of the function, and delta x will simply be the total width, b minus a, divided by the number we want, which is 5. And we just add all those up, and we get an approximation for the area. If I want to improve that, we simply make more and more rectangles. The more rectangles we make, the more work it'll be, but the closer we will get to the area under the curve. And what we're going to say is as n goes to infinity, the rectangles will get vanishingly small, but they will now represent closer and closer the actual area under the curve. This process is what we mean by integration. So in the limit as n goes to infinity, where we're starting at a, ending at b, the area will be the limit as n goes to infinity of this sum, which is the area of the rectangles, from 1 to n, of the function evaluated at each of the x's, that's the height, and delta x is the width of each of the rectangles, which is the b minus a divided by n. We're going to represent this limit right here with this notation. This stretched out s right here is going to replace the Greek letter sigma for sums. This means the integration process. F of x is what we're going to call the integrand, and dx tells us the variable of integration that we're using. We will use but not prove the following. Namely, that to evaluate this, we need to find a new function, capital F of x, which is known as the antiderivative of the original function, little f of x. And if you take this new function, this antiderivative, and evaluate it at the upper limit, and subtract the same function evaluated at the lower limit, you get the area under the curve. This is something we will take. You will prove this in calculus. I am not going to attempt to prove it here. So basically what we want to do is find a function, capital F, so that its derivative is in fact the original function. F of x, capital F of x, will be called the antiderivative of the original function. Now, derivatives versus integrals. Hopefully you've already done enough derivatives in math that you realize the derivative is basically the slope of a curve. It's the instantaneous rate of change. It also, note, involves taking subtraction and division. Those give us a derivative. In integration, we're doing the opposite. We're adding things up, that's what this sigma right here is, and we're multiplying things together in order to get the area as opposed to the slope. So this multiplication gives us the area of the rectangles. Adding them all up gives us the overall area under the curve. So in a sense, integration is the opposite of differentiation. Another point is that when we're above the x-axis, we're going to call that area positive. When we are below the x-axis, we're going to call that area negative. So the area can, in principle, be negative. Now, let's look at some examples to how we actually find an antiderivative. The only thing we're going to worry about right now are using polynomials. So we'll take our original f of x to be a simple polynomial, 3x plus 2, and we want to find a function whose derivative is this f of x. And we're going to call that capital F of x. Well, to get x as the derivative, we have to start with x to the second over 2, because we take the derivative of x to the second over 2, we get x. To get a constant term, we want x to the first over 1, because we take the derivative of that, we get a constant. But we also have to add an arbitrary constant at the end, because we take the derivative of any constant, we will get 0, and implicitly there's a plus 0 here. So this function right here is our antiderivative. we take the derivative of that, we get 3 halves right here. Then this is 2x to the first plus 2x to the 0 plus 0, the derivative of the constant. That gives us, as the 2's cancel out, 3x plus 2, and that is our original function. So this right here is the antiderivative of this. Now what I want you to do for practice is find the antiderivative of this second function right here. Pause the video and find the antiderivative of this function. Oh, here it is. It's x to the fourth minus x squared plus, again, this arbitrary constant c. Because we take the derivative of x to the fourth, that's 4x cubed, which is what we have right here. Derivative of this is minus 2x, which is what we have right here. Derivative of x is just 1, which we have right here. Derivative of the constant term c right here is 0, and implicitly there's a plus 0 here. So this right here is the antiderivative of that. Now, the reason we find antiderivatives is really to find areas, which is what we really want to do, or find areas under curves. So here we will take our function, which I've graphed right here, as minus 2x squared plus 8x plus 1, and we want to find the area from x equals 1 to x equals 3, which means we want to evaluate this integration right here. And in order to do that, we need to find the antiderivative of this function. And here is our antiderivative. You can take the derivative of this and verify that, in fact, you get the original function back again. Then we need to basically evaluate this function at x equals 3, and again at x equals 1. And I've written them down here. It's 21 plus this constant c, minus 4 1/3, again, plus the constant c. But notice the arbitrary constant doesn't matter because it cancels out. We have c minus c. And the final answer ends up being 16 2/3, which is the area under this curve. That's if we want to do it analytically. We can also use our calculators to do this. On your TI calculator, there's a button called Math. Hit that button and you get a menu. One of the items on the menu is, in fact, to evaluate an integral. What you need to do is enter in the function right here in this form, minus 2x squared plus 8x plus 1, then comma, and you need to tell the calculator that you're integrating with respect to x, and then comma, you put the lower and then the upper limit, and then close the parentheses. That's just the format you have to enter that in. Hit that, you should get the answer, 16 2/3. I would suggest doing that to verify that you can get that to work. Another way to do this, which is probably a little more straightforward, which kind of looks like this, is you literally graph the function on your calculator, which means you enter y equals this function and graph it, making sure that your limits go something like from 0 to 4, so you have your limits displayed on your screen. Once you do that, one of the options right under the screen is this calc function, so hit second calc, and one of the options under that menu is, in fact, to find the area under the curve. And what you need to do is enter the limits, which is 1, and then enter, and then the second limit, 3, hit enter. That should evaluate the area from 1 to 3, and again, should give you 16 2/3. I would again suggest that you do that on your calculator to make sure you see how it works. Any one of these methods should give you the correct answer.